Power. There we go. Nobody knows what we talked about. See? No evidence. Power is defined as the work done divided by the time. And work is actually, the unit for work is what? Joules. Time is second. But 1 joule second, we decide instead of calling joule second, that looks stupid there. We go watts. Equals 1 watt. So for unit, you'll see me use W for power in watts. So when you buy a light bulb, it says 75 watts, 100 watts, 200 watts. That's the power. Now, if you're buying if you have a pool there and you buy a motor, they don't measure the power in watts. That's too small. They use what? Horsepower. 1 horsepower. I'm missing the O, I knew that. I need to go to bed too. 1 horsepower is equal to 746 watts. Some funny number. One horsepower is equal to 746 watts. So when the numbers start to get large numbers, we switch the power, we start calculating horsepower. For example, our brain uses about 20 watts of power when we're thinking. That's it, 20 watts. If you walk in the stairs, 150 watts. TV, 200 watts. Stove at home, 120,000 watts. Car moving at 40 miles per hour. You were asking about car moving at 40 miles per hour or 60 miles per hour. At 40 miles per hour, look at the power in it. 70,000 watts of power. That sounds a lot. Till you look at Hoover damp, and that's 1.34 times 10 to the 9th, some massive number. That's how much power you can get out of that. Imagine how many light bulbs can you light. This is what the Hoover damp actually can get power. 1.34 times 10 to the 9th. Just if you don't understand what that is, divided by 75. Most people have 75 watts light bulb at home if we're not using the newer ones now. We're going to see how many light bulbs can you light. You can have that many light bulbs lit at the same time, the power you get from Hoover damp. $17,866,667.75 light bulbs lit from just that water coming down. All day, 24 hours a day, 7 days a week. That's why the push for different source of power, wind power. If you live in a section there's a lot of wind, you see these windmills. Actually, one windmill can light the whole Springfield here, the section where we are right now, the college here. You can light every single building, air condition, everything, with one of them. Now, if we think that's a lot, try nuclear power. Till we have a problem, then we got an issue there. But if we design them correctly and safe, and hopefully we wouldn't have a problem with it, like the Chinova problem there, then we can have electricity dirt cheap. You don't need that solar on your roof. That's ugly looking one, So let's see how we're going to calculate power. We have a slow-moving truck in front of us, and I can't take the car in front of me, even if it's moving fast. Something about them, I got to pass them. We'll say this is a bread truck in front of us. I'm right behind them. And My car has a mass of 1,300 kilograms, so that's like a Suburban, good sized car. And I got stuck behind the person. I couldn't take it. I said, forget about that. I stepped on the gas. I give my car. So my initial speed of the car was 13.4 meters per second. That's roughly 30 miles per hour. I said, I gotta pass this truck. I gotta pass this truck. I can't take it. I step on it, and now I'm passing the truck, and I'm going at a speed of 40 miles per hour. That's the driver again. 40 miles per hour, that means roughly 17.9 meters per second. So initial velocity was 30 miles per hour. We can relate to that. You go to final velocity 40 miles per hour to pass the truck. And it took us 3 seconds to actually get the speed to go from 30 to 40 and pass that truck. 3 seconds. That's it. What is the minimum power required for this pass? The minimum power required. To make the pass. When I say the minimum power required, in addition to what I had going to the car here, there was some power going to this car. How much more power I need to give this car to pass that truck? That's what I'm asking. Well, power, since we're looking for power, I'm going to leave a space here. I'm going to say, well, power is the work done divided by the time. How long it took me to pass that truck? How much time? 3 seconds? Well, how much power did I use to pass that truck? I don't have that. Can I find it? Go back 2 sections earlier. We talked about work done is the change in kinetic energy. Which is what? 1/2 mass times the final velocity squared minus 1/2 mass times the initial velocity squared. So 1/2, the mass of my car, which is 1,300. What's the final velocity today? 17.9 minus 1/2. 1,300, what's the initial velocity? 13.4 squared. And I get that number to be, if I push all the right buttons, 91553 joules. So how much power? Let's divide them. 91553 divided by 3, which is 30,518 watts. Now, if I don't like to use watts, I can change it to horsepower. 1 horsepower is equal to what? 746? So the power equals 30,518 over 746. Roughly 40.9 horsepower. That's how much power was required. Now, a lot of times you look in some physics book and they write the equation for power a little bit different. Let me explain what I mean by that. Power, we said, is what? Work divided by time. Well, the first thing to do when we start talking about work, we say work is what? Force times what? Distance divided by the time. Well, what is distance divided by time? That's velocity. Yep. So power is really force times velocity. That's an equation that you see sometimes for power. It's the force times the velocity. So let's take a car going up the road here. We have a hill here, and we got a car going up that hill. The force required, we have a force of 1,450 Newton to keep this car, which is 1,300 kilogram car again, moving with constant speed up a slope, moving with constant speed. And the road makes an angle of, I don't know, 5 degrees you want to use. Now, if the engine of the car delivers supplies, what are we going to do? How much? 40,000 watts? 40,000 watts, roughly, about 55 horsepower, I think, 746 is it? And make sure that's doable in real life. I don't want a number like 8,000 horsepower. Let's see, 40,000 divided by 746, 53, 54 horsepower, yeah. Every car has, I hope every car has more than 53 horsepower, unless you got one of those little tiny cars, like a bicycle, with the things around it, you know. What is the maximum speed of the car? What is the maximum speed? Notice I can use that equation I just gave you here. I just derived that equation. Power equals force times velocity, or speed. Do we know what the power is? Yes, 40,000 watts. Do we know what the force is? 1450 times the velocity. Can we get the velocity of the car? Roughly 28 meters per second. About 62, 63 miles per hour, roughly. So notice that angle here didn't come anywhere in the problem. I just put that to make the story nicer. I could have made any number here for that angle. Once I give you the power and the force I can use that equation to calculate the velocity. If I give you 2, I can find the third one. Now, if the force wasn't given to me, then I gotta figure a way to calculate what that force should be.
Professor?
Yes?
So I have a question regarding the units that we're using. We have W for weight, for work, and for watts. Is it going to be like differentiated in the problems so that we know exactly which
Well, in the problem they state this is the power is. So if they said the power, you know, that's watts.
Mm-hmm.
You know, the work, if they say the work, find the work, that's W for the work, you know. But the units, that gets really confusing because you'll see them showing up in different places. P for power. It's going to show up something later down the course also. P equals M times V. You go, what? Something, or L equals M times V, angular momentum. So some of these units repeat itself the same letter. And sometimes they have to use capital letters, lowercase, uppercase. But I was looking here, I'll be honest, I didn't see them using lowercase or uppercase for work or watts. They use W. The only thing they're doing for work is they just write like W with something else with it. When they write the work, they go, work by car. So you know it's not watt. So they're adding a subscript to it to let you know that's work, you know. But you're right, is W, is that work? What is it, you know? Is it watt? Work, when you write it there, it's hard to tell when you look at it. So a subscript sometimes is nice. I type work done by the spring, work done by the normal force, work done by gravity, like we did early, to let you know that's what each one is. The total work initial value I was doing earlier. Where is it? Kinetic energy. Notice I wrote work, initial work by the spring, final work by the spring. You know, so you know what that is. We did that one, okay. That's it, I think that's the last topic.